Right. So, we will move on to stochastic differential equations. Right. So, we have been looking at the diffusion equation. So, we have been looking at the diffusion equation, let us say del p x comma t, del t is d del 2 p del x2. Right. So, we derived this equation start as the continuum limit of the random walk, and then we looked at various biological applications where the diffusion equation becomes relevant, whether it is structure of polymers or motion of proteins and so on and so forth. And what the diffusion equation tells me is essentially this quantity, if I were to solve it, p of x comma t, which is the probability of your random walker or your diffusing particle to be at some position x at some time t, right. But if I were to say that, well, what is the trajectory of a given particle, right? So, if I have some particle which is doing a random walk, and it traces out some path as it moves, the diffusion equation will not tell you what are the sample trajectories of this diffusing particle, right. So, the sample trajectories are stochastic. So, the sample trajectories are stochastic, right. Their probability evolves according to this equation, the diffusion equation, but the trajectories themselves are stochastic. And if you think about the sample path of a sample trajectory of a particle which is undergoing diffusion, so these sample trajectories are continuous everywhere, but also non-differentiable everywhere. Okay, so these are also non-differentiable everywhere. All right, and how do I go about seeing that? So, let us calculate a few things. So, let us try to first calculate this probability, that let us say I am here is my random walker at some time t. Okay. So, at some location z at some time t, and I want to ask what is the probability that it escapes some region of size epsilon around it. Okay. So, essentially what I want to find is this probability, that what is in time delta t. So, in time delta t. Okay. So, essentially what I want to find is this probability, that what is p of x comma t plus delta t, given that it was at some location z at some time t. Okay. And I want this probability of escape, which means that I want my x to be outside this radius, right. So, therefore, what I will do is that I will integrate these probabilities over all values of x such that x minus z is greater than epsilon. Is this clear? So, I am asking what is the probability that a particle escapes a region of size epsilon, provided it started at z at some time t. So, I write down the probability distribution p of x t plus delta t given z at t, and I integrate over all values of x such that this x minus z, this difference is greater than epsilon. Okay. Because this is a diffusing particle, I know this probability distribution, right. So, because this is a diffusing particle, so I know what is p of x t plus delta t given z comma t, right. What is this? What is the form of this probability? Huh? Gaussian. So, this is e to the power of minus some x minus z whole square by 4d delta t and then 1 by square root how much 4 pi d, right. So, this remember we are talking about a diffusing particle. So, I know the probability distribution because we have solved the evolution equation for the probabilities. Alright. So, then it is a question of simply plugging this probability over here and evaluating this integral. So, 1 by square root 4 pi d delta t integral e to the power of x minus z whole square by 4 d delta t dx, and I integrate over from epsilon to infinity, right. So, this is x minus z equal to epsilon to infinity, and if I do a change of variables, let me call it u, then this is just u square, this is du. So, I have just done u equal to x minus z, right. So, then this integral goes from epsilon to infinity e to the power of minus u square by 4 d delta t. What is this? So, let me do one more thing. So, let me call this whole thing as some y. So, let me say y square is u square by 4 d delta t. I get dy is equal to du by 2 root d delta t, right. So, then this becomes integral e to the power of minus y square dy. I have just a 1 over root pi left, and then this is u was epsilon. So, epsilon square by 4 d delta t to infinity. So, this is right, I hope, root pi, I suppose. Okay. So, again, so what is this? So, this is the probability that in some infinitesimal interval of time delta t, I have escaped a neighborhood epsilon of this of my initial position. Okay. And then in the limit that delta t goes to 0, this lower limit also approaches infinity, right, because you have an epsilon by 4 d root delta t. So, in the limit that delta t goes to 0, you get this integral as this integral approaches 0 itself, right. Because the lower limit approaches the upper limit, so the integral itself approaches 0. What does this say? So, therefore, this says that my trajectories are continuous. So, therefore, this says that my trajectories are continuous, right. If I have started at some point in some infinitesimal time delta t, I could not have hopped out, I have to go through a continuous path. Okay. So, this tells me that although my sample trajectories are stochastic, they are continuous everywhere. Okay. On the other hand, we can show this. Is this clear? Okay. On the other hand, we can show this, that although they are continuous, they are also non-differentiable everywhere. Okay. So, that is we can calculate the velocity. So, we calculated the position. So, let us ask that what is the probability? What is the, so let us ask probability that your velocity, your absolute value of the velocity essentially is larger than some value k, okay, some number, whatever sum that value. Okay. So, I want to calculate this quantity next, because what is it saying? So, essentially I had this path, I have come here, okay, and I am calculating, is there any probability that in some unit infinitesimal interval of time delta t, it could have gone to over there and then started again. So, I have defined this neighborhood, and I am asking, is there any probability that a path which comes here at z at time t goes to z plus epsilon at time t plus delta t in the limit that delta t goes to 0? And I say that no, that probability is 0, which means that it must be infinitesimally close to this, because it is independent of epsilon, right. So, it must be infinitesimally close to this where it was at the previous instant of time, and therefore, the trajectories must be continuous. They must be evolving continuously. Is it clear? This is the path of a diffusing particle. The probability is evolving according to the diffusion equation, but I am looking at some particular sample trajectory of this diffusing particle. Okay. And I am asking that whether these trajectories are what characterizes these trajectories. So, I just wanted to show that these trajectories are continuous, and this is the proof of that in some time delta t you are forced to be infinitesimally close to where you were at the previous instant of time, which means that the trajectories are continuous. Next, I want to show about these velocities, and I have asked that what is the probability that this velocity, this larger than some number k, the absolute value of the velocity. Okay. So, to do that, so essentially mathematically what I want to find out is this probability that x at time t plus delta t minus x at time t divided by delta t, right. That is my velocity dx dt. And I want to ask what is the probability that this is larger than some number k. Or again, so therefore, what I want to ask is what is so this is equivalent to asking that what is the probability that x at time t plus delta t minus x at time t is larger than k delta t. Right. And again, I know how my probabilities evolve. My probabilities evolve like a Gaussian. So, in time delta t, so if I calculate this, so this is nothing but again e to the power of minus u square by 4 d delta t, and in this case it is greater than k delta t. So, it is going from k delta t all the way up to infinity, right, and of course, normalization. So, 1 by 4 pi d delta t. Okay. Again, so the probability. So, what is the probability distribution of the displacement x t plus delta t minus x t? That is a Gaussian, right. So, it is e to the power of minus x t plus delta t minus x t whole square by 4 d delta t. I just call that thing as u, and then exactly what I did here. Okay, and again I do the same thing. I call this thing as my y, and then I substitute back. So, I call this y square as u square by 4 d delta t, and then I am left with e to the power of minus y square dy 1 by root pi, exactly the same as before, except my limit now my u was k delta t earlier, because that is my difference. So, this is k square. So, this is k square by 4 d times delta t square root, right. Is that correct? K square by 4 d delta t on the numerator, and this thing in the limit that delta t goes to 0. So, this is just this integral, right. So, this is integral 0 to infinity e to the power of minus y squared dy 1 by root pi. This is just my Gaussian integral, and this is half. This is half. So, with probability half, this displacement is greater than k. If you look at the reverse, because this is modulus of velocity, So, with probability half, it will be less than minus k, exactly by the same thing. So, therefore, with probability 1, your the absolute value of the velocity. So, this absolute value of the velocity is larger than whatever number k that you choose with probability 1. With probability 1. What does this mean? That means that this instantaneous velocity does not exist, right? Because it is infinite, because I can choose k as any number and this velocity would be larger than that number. So, I calculated this. I could calculate this other thing as well, that what is the probability that x of t plus delta t minus x of t by delta t is less than minus k. That would also work out to be half, exactly the same calculation. Therefore, this modulus being greater than k would be probability half plus half, which is 1. Why doesn't it depend on k? So, that's the property of the sample trajectory that we are showing, that when you have this particle undergoing diffusion, these trajectories that they trace out, these are non-differentiable. But this proof, when I am proving this, this is independent. This is independent of whatever value of k that I choose, right? So, this thing I have proved generically for any value of k, right? Now, I can put the limit that k is large. I suppose it is a subtle point about how one takes the limits. But generically, when I am doing this proof, I am doing this for some constant value of k, and therefore, for that given value of k, I can always take delta t small enough that this goes to 0 to infinity, and therefore, for that value of k, the probabilities becomes half, and then I can do this for any value of k. It is in some sense what this is saying is that this velocity operation, this dx by dt, is not a valid operation to do for these sort of for trajectories that are governed by the diffusion equation. This operation itself is not because these paths are non-differentiable. So, essentially what it boils down to. What it boils down to is saying is that this dx by dt, this does not exist. Although the trajectories are continuous, they are non-differentiable, and therefore, this derivative dx by dt does not exist. What that means is, therefore, in contrast to what I would do in ordinary mechanics, I cannot write down an evolution equation for this coordinate of this part of this diffusing. Generally, what would I do? I would write down some equation of motion, right? Dx of dt is some f of x. I would solve this equation and say that what would be x as a function of some time at some future time. I can go from here to here, Which one? Because it is non-differentiable, because that is what we proved, right? The velocity is the derivative of the position. So, that blows up. So, therefore, the paths are non-differentiable, and therefore, this dx by dt does not exist. So, I cannot write down a standard ordinary differential equation like I do to solve for the evolution of these sample trajectories. So, it is not that you tell me where it was at some time x naught, and I can solve some equation and tell you where it would be at some future time. So, that is why this. We cannot write the differential equation, but so we will write some equations. What is what do you mean by the displacement equation? So, that is what we will try to do. So, that is the point. So, we cannot write down an ordinary differential equation like this, because my paths are non-differentiable. We will do something different, which is called as the stochastic differential equation. So, that is what we will try to write down. No, I mean, you have some probability of x's, I agree. You can find I can find the probability current, like we wrote down the Fickian current, but the canonical way. So, we can write something analogous to this. So, that is what we will try to do actually. So, we can define some sort of a analog of the velocity for these differentiable paths. So, let us try to do that and then we can see what that means. P of yes. For a, as long as you are careful with the definition of the velocity. So, yes, I mean of course, people write velocity distributions and so on, but you have to be a little careful as to how you are defining the velocity. So, all right. So, that is what we will sort of try to do. So, we will sort of think about when you have these sort of trajectories which are formally non-differentiable, how do I sort of formulate analogues of my differential equations in this case and therefore look at evolution of trajectories.
And in this, if we take the values which are these key values which are lesser or more than the extreme values like minimum or for example, the minimum velocity of particle, there is a limit. So if we take k less than that, then the probability should be 1.
So, remember what is in some sense, remember what are you doing. So, what was I doing? I was doing a random walk. So, I had a particle at every time I made a decision as to which direction to take a path step in and I took a step. Next instant of time I took another decision, I took another step. I generated these trajectories which in the continuum limit when your delta t is very small look something like this. Okay. Fundamentally these are like hops. So, these are how these trajectories are getting generated. Okay. So, this is, there is no velocity limit that I have started, there is no definition of the velocity that I have started with. I have just started with that definition of the random process. I am taking, it is a hopping process, every instant of time I choose a direction, I make a hop. Okay. In the continuum limit, it looks as these continuous trajectories, the probability evolution is governed by that, but still the paths, trajectories fundamentally are non-differentiable trajectories, are non-differentiable paths. So, there is no fundamental concept of velocity or any restriction on velocity that I have introduced. Right, because the process that I have defined has nothing to do with velocities. You can use it to model of course different physical or biological processes where you can define a velocity that you intuitive velocity, but formally at least I have not started with any definition of velocity. The process is just that hopping process in the background. Okay, so that's what we'll try to do. We'll try to, although dx dt does not exist, we'll try to write down some analog of these ordinary differential equations. So, let us just recap what we do in an ordinary differential equation. So, I start with something like that. So, I have dx dt, some evolution equation is equal to f of x, right. What we can do is that we can convert it into a difference equation. So, x of t plus delta t minus x of t is f of x times delta t, right. So, for small values of this time interval, I can interpret this differential equation as a difference equation, right. And then if I'm simulating this process in some time interval 0 to t, let us say, I can break this up into small chunks of time delta t, let us say n chunks, each of size delta t, right. And then I can write down my trajectory. So, x n, let us say, is x of n times delta t, right. And then x of n plus 1 is x of n plus f of x n times delta t, so on. And therefore, x at time t is x naught plus f of x I delta t sum over I equal to 1 to n, right. This is the standard way, if you are given a differential equation, or if you want to write it in an integral form, then this is x of time t is x naught, your initial position, plus integral f of x, let me call it something else, f of s ds from 0 to t, right. So, this is my prescription for the standard ordinary differential equations. Now, for these sort of diffusing particles, where the trajectories are non-differentiable, we can define something analogous. So, we had something like this. X n plus 1 was x n plus f of x n delta t. So, similarly, I can write x of n plus 1 minus x n is equal to something, some increment delta w of n times some prefactor square root 2d. We will see why we need the square root 2d to recover the diffusion. But let me say that I write down an evolution equation, a difference equation in this form, exactly like I had here. X of t plus delta t minus x of t was something times delta t. Here I have something times delta w, where I will define what this delta w is. I have not yet defined. Exactly like that, right? So, except I have introduced here this new quantity delta w of n. Okay. So, what is this delta w of n? So this delta w of n, for all values of n equal to 0, 1, 2, so on. These are independent. And identically distributed. IID. That's what we call it, right? Independent and identically distributed random variables. These are random variables with a given probability distribution, which is a Gaussian. Okay. So it's a Gaussian with random variables, and the probability distribution of delta w of n. This is a Gaussian with zero mean, and standard deviation and variance, which is sigma square is delta t. So, I am back constructing in some sense. So, I am defining this process, and I will show that if I were to work this out properly, this will recover for me my diffusive works. Okay. And those of you who have done advanced StatMech will know what this delta w is, hopefully. Right? What is delta w? Who is doing advanced StatMech? What is delta w? No? Already? I should tell Amita. Anyway, so this is a Gaussian with zero mean, and this variance sigma square is delta t, okay, which means that this p of delta w n is what? E to the power of minus delta w whole square by 2 sigma square. So, by 2 delta t, right, 1 by square root 2 pi delta t, right, 1 by square root 2 pi sigma square. So, 2 pi delta t. So, I evolved my positions according to this equation, this difference equation, that x of n plus 1 minus x n is square root 2d times this random variable, and this random variable obeys this probability distribution, that it is a Gaussian with variance delta t and 0 mean. So, therefore, again if I were to do exactly like this, if I were to iterate, I will get that x of n is x of 0 plus summation over square root 2d delta w I, okay, sum over I equal to 0 to n. So, I start with x0. Every time I choose this random variable according to this probability distribution, I update my x, and I do this again and again. I get this x of n. Okay. Let us say it does not matter. Let us say for the sake of simplicity, I start at 0. I always start at 0. So, Alright. So, what I want to know is what is the probability distribution for this x of n, right. Now, that is simple enough. I know that the probability distribution of this delta w is a Gaussian. My x of n is a sum of Gaussians and that is itself a Gaussian, right. So, because it is right, everybody knows. So, as long as I find out what is the mean and the variance, because Gaussian only has the first two moments, as long as I find out only the mean and the variance, I know what is the probability distribution for x n, right. So, I will find out the mean and the variance. What is the mean of the sum of, if I have a random variable which is the sum of n random variables, what is the mean? Mean is 0. Generally, the mean is the sum of the means, right. If those means are 0, in this case of course 0, because you have Gaussian with 0 mean. So, good. So, average x n therefore, average x n is therefore 0, right, because the mean of the sum is the sum of the means. In this case, each mean is 0 and therefore, your average x n is 0. What is the variance of the sum? Sigma square of x n is the sum of the variances again, and therefore, this is there is this 2d over here. So, 2d n times delta t, because each variance is delta t. There are n summations. So, n times delta t, there is a square root 2d sitting in front. So, therefore, I have 2d n delta t. N delta t is what? N delta t is my total time that has evolved 0 to t. So, this is 2 dt, right. And therefore, if I wanted to write what is the probability distribution for this x of n, what is this? This is just e to the power of minus x n square by 2 sigma square. So, 4 dt by 1 by square root 4 pi dt, right, which is exactly the solution of my diffusion equation. P of x at time t is 1 by square root 4 pi dt e to the power of minus x n square by 4 dt, right. So, what we have done using this construction is to define my increments in such a way and with the correct, and so here you can see why I needed that square root 2d, because I want a 2d over here. So, by constructing my increments in this way, I have found out a finite difference scheme which will recover for me my solution of the diffusion equation for the probabilities. Okay, everybody is happy till here. Okay. So, now once I have done this, I can construct this continuous time process. So, I was writing this in discrete time intervals, but I can now take the continuum limit of this and I can construct the corresponding continuum continuous time process. So, this is not needed anymore. So, what I have is if this x n, right. So, I have x at time t essentially is sum over I equal to 0 to n delta w I, right, square root 2d of course, and in the limit I want to take this limit that n goes to infinity. N goes to infinity such that of course, so I want to take the limit that n goes to infinity, delta t goes to 0 such that n delta t is finite and goes to t, right, because that is my final time. So, this is how I take the continuum limit, my standard way, delta t goes to 0 and goes to infinity. Okay. So, this is what I want to do. So, essentially the summation will become an integral. So, x of t is square root 2d integral 0 to t, let me call it some dw, that delta w I call it as some dw of some s, or if you want, and so this we can write as some square root 2d, this w of t, and this w of s that I have constructed right now, right, this is called as the Wiener process. Have you done Wiener process? No, you've done the Wiener process. Okay, then it's fine. So this W of S is called the Wiener process. Or standard Brown or pure Brownian motion. Pure. So it's a Gaussian process with independent and stationary increments. So every increment is independent of the previous increment. It has 0 mean, and it has a variance which is proportional to the time. So it has a variance which is proportional to the time. Right. How is that different from which one? Sorry, this one. So this is exactly the same thing. So if I, it's just that instead of defining in terms of a summation over discrete a's, I've just taken the limit that delta t goes to 0 and defined it in terms of an integral. But if I write p of x comma t, that is exactly that, that Gaussian e to the power of minus. Okay. All right. So therefore, this provides a definition for Brownian motion. In fact, this provides a definition for Brownian motion. This is the continuous random process. This is a continuous random process such that this family of random variables that I have, W of t, for all t, all positive values of t, this is Gaussian. And it is Gaussian with 0 mean, W of t, mean W of t is 0, and an autocorrelation function W of t, W of s is minimum of t comma s. So, if you take this expectation value, a Wiener process at time t, a Wiener process at time s, you can show that that comes out to be the minimum of this t comma s. And that is easy to show, I guess. So, remember the Wiener process, the variance is proportional to the time. So, if I want to calculate this correlation function, W of t, W of s, right? These are two time instants, time s, time t. So, if for example, my t was greater than s, okay, then let me calculate this thing, that W of t minus W of s with W of s. Okay, so I want to calculate this, but I'm starting out by calculating this completely different quantity, Wt minus Ws. So, a Wiener process, so one Wiener process up to time s, and then another Wiener process from s to t. Okay. Because these are independent, I know that this correlation function must be 0, right, because this happened up to time s and this happened after time s, because I have taken this assumption that t is greater than s. So, therefore, these two must be uncorrelated, and therefore, this I must have as 0. And now I can break this. So, now this gives me a Wt Ws expectation value minus Ws whole square, which is 0, but this I know is S because this is a Wiener process. So, therefore, W t W s is S in this case, if t was greater than S, this thing. So, remember when I am doing these Wiener processes, I take an increment delta W from the distribution. The next increment that I choose is completely independent of the previous increment. There is no memory. That will lead us to Markov processes, maybe next day, not today. But essentially, so if I am talking about time increments where there is no overlap, if there is overlap, then of course there is some correlation. As long as there is no overlap in the times, these are completely uncorrelated because these are independent variables. And therefore, here when I am looking at the correlation of this is 0. So, this is some Wiener process from 0 to S. This is another Wiener process from S to T. Okay. So, there is no overlapping time period. So, therefore, this expectation value of this is 0. Here, because I want to know I have a Wiener process from 0 to T, I have a Wiener process from 0 to S. So, 0 to S is one, 0 to T is another. So, there is an overlapping time period, right. So, that is what we are showing, that in this case the expectation value is the minimum of that, whichever is the minimum, that is what we are trying to show. So, there is an overlapping time period, which is why that is the autocorrelation. Only delta W's are independent, but as long, so this is, so in that sense if I am thinking of W of S, which I have constructed from 0 to S, this is constructed of these delta W's which are independent, but then I have something which is S to T, then that is also constructed of something, but there are no overlapping delta W's. So, there is no correlation therefore. So, this arises from the independence of the delta W's. This thing? What? Sorry? Oh, that we showed, no, that the variance is proportional to the time, right. So, S is the time, I mean, you can call this T1 and T2 if S is confusing. So, T1, T2. These are just two time indices. So, when you are looking at correlation functions at two times, this value is always equal to the smallest time. It is a diffusive process, yes. So, at some level it is a diffusive process. You might have to find the correct mapping in some sense, or if, but so this is all related to this x square of the random walk that we had calculated goes as t to the power of 1. This is all related to that. So, yeah, at some level it is a diffusive process. Okay. Yes, idealized run and tumble. If you were to actually go to a bacteria and calculate this, you will see deviations from this, but an idealized run and tumble is this variance going as t. Real bacteria you measure, you will see differences. So, you can then speculate what those differences are due to, but the ideal run and tumble particle is this. Okay, right. So, this was pure diffusion. This is pure diffusion of a particle doing a random walk. The next step would be to think about a particle which is moving under the effect of some external force, right. So, let me think about, so I consider a particle moving in a fluid environment, under some external force, okay. So, what does I have this particle, it is immersed in a fluid. Okay. What does the fluid do? So, what does the particle do rather? The particle as it moves will collide, and there is of course some external force F, right. So, as the particle moves, it will collide with these fluid particles, right. There are many fluid particles. Okay. What these collisions do is that in the absence of force, it would have given rise to some diffusive motion of the particle, Brownian motion, right. But it will also generate for you an effective frictional force that will oppose this motion induced by the external force as well, right, in a dissipative sort of, this is a dissipative system, right. So, if I, for the time being, if I ignore diffusion, so there is diffusion, collisions with fluid particles gives you diffusion, and it gives you a frictional damping force. So, if for the time being I ignore diffusion, then what I would have is m d2x dt2, right, plus gamma dx dt is some f of x, whatever is your external force. Gamma is my friction coefficient. Gamma is my friction coefficient. So, I will put it back. Remember, diffusion is non-differentiable, so I could not have written down an equation like Newton's laws of motion. So, let me just write down equation and then I will add back this non-differentiable part. So, now generally why do I say fluid? Because generally all biological systems are mostly moving in some fluid medium, and in these sort of mediums, given the size scales of biological objects, cells and proteins and so on and so forth, it turns out that the inertial term is very small. Okay. This is called as the low Reynolds number regime. This is called as the low Reynolds number regime. Low Reynolds number is essentially, so this is fluid mechanics. Reynolds number is essentially a measure of how strong your inertial forces are. Inertial forces are compared to viscous forces, and for biological systems, mostly the inertial forces are very weak. So, therefore, when we look at biological systems, we will often just neglect this inertial term m d2x d2, m d2x dt2. This is also called as the overdamped limit. This is called as the overdamped limit. Okay. So, viscosity is very high, which is the situation inside cells and inside tissues and so on. You can work in this overdamped limit. That is the correct physical description of the system. So, then what I have is dx dt, dx dt. So, this is my evolution equation is fx by gamma. Let me call that a of x. A of x. Okay. Okay. So, this is my analog of the ordinary differential equation that I had. Dx dt is f of x. In this case, this f of x or a of x that I have written is the force divided by the friction coefficient. And therefore, if I were to write this increment dx, it would be ax times dt, right. All right. So, now that I have worked out this part, this deterministic part, I will put back diffusion, and I know how to put back diffusion. So, what will I put here? I will put square root 2d times a dw, the Wiener process, right, dw of t. What is this? This is the Langevin equation. Have you done? No? Yes? Yes, no? This is the Langevin equation. So, this is the stochastic differential equation This is the stochastic differential equation for overdamped motion. Stochastic differential equation for overdamped Brownian motion. Sometimes in the physics literature, we will write this as a differential equation actually. So, we will write this as a differential equation dx dt is a of x plus xi of t, right, where the xi of t has this property that the mean value of xi of t is 0 and xi of t prime is delta t minus t prime. So, this is white noise. So, this arises purely from this property of the Wiener process that average W is 0 and average W square is equal to T. From there you can, although this has to be interpreted carefully, like I was saying, we write it as a differential equation, but you have to remember that the trajectories are actually not differentiable. So, although I write a dx dt, where it has a deterministic part which is a of x, which is coming from an external force. It has a stochastic part xi of t, which has this white noise characteristics. It is delta correlated, 0 mean delta correlated, but it arises from this sort of stochastic differential equation, and this is the correct way of looking at that equation. So, even if we write it this way, the way you should interpret this is as in this form, that there is a dx increment, the paths are not differentiable, therefore, this dx dt I should always multiply by dt and then interpret that equation. So, I don't know, I have to work it out. So, so we had xi of, not xi, sorry, we had this thing W of t, W of s as minimum of s comma t, right? That is what we had. This we can write as in terms of Heaviside. So, S Heaviside of x is 1 if x is greater than 0 and 0 if x is less than 0, right. So, I will have S when S is less than t. So, that means Heaviside of t minus S, and I will have t when t is less than S. So, Heaviside of S minus t, right. That is, so it is the same, sorry, I am not sure if you can see. So, this I had that this is minimum of S comma t. This minimum I have written down in this terms of this Heaviside. Now, I can take a derivative with respect to t. Derivatives of Heavisides are Dirac deltas, right. So, if you take a derivative with respect to t, again we will have to take a derivative with respect to S, then you will get a delta of t minus S. Yes. So, this follows from therefore the property of the Wiener process itself. All right. So, what we have done is that we are working with this diffusion equation. Now, instead of thinking about the probability distributions, we think about the underlying trajectories that generate for me this probability distribution. We showed that the right way to think about these trajectories is as these sort of non-differentiable paths. And then if I wanted to write down an evolution equation for these trajectories, the correct way to do that is in terms of this Wiener process which has this 0 mean and variance proportional to time, right. So, in some sense this dw is like proportional to root of time. So, here I have time, here I have root of time, right, because the variance is proportional to the time increment. And in this way you can write down these sort of Langevin equations for these processes and then study the evolution of individual trajectories. Okay. All right. So, having said this, this Wiener process is an example of this process where you have no memory. Every increment that you do is completely independent of what happened to the process at all earlier instance of time. This is something that is an example of a Markov process. So, what I will move on to is trying to construct probability distributions of Markov processes, and from there on write down the master equation for a generic stochastic process. But let me do that next day, because otherwise I will. Yeah, so let me do that next day. So, otherwise I don't want to start and then have to stop. Anyway, this is somewhat different from what we have been doing. So, it is good to take time to digest this sort of stochastic differential approach to trajectories. Yes, in the ordinary differential equation setup, or in this? Yes, yes. X. So, I mean, the distance covered is the sum of the displacement. So, I had this dx of dt is f of x. This equation you are saying. So, this is just x at time t plus 1 minus x at time t is f of x times delta t. So, therefore, this thing is the displacement from time t to time t plus delta t, and that is just given by this. So, it is exactly like what we have had over here, this f of x being this f by gamma, essentially same equation. Just like the evolution of the positions of your random particle. This equation describes the position. This difference is of course the displacement in time delta t.